So hi guys. So this talk is about a paper that was with Simran Kaur, who is an undergrad here at CMU, and Yuanja, Zico, and Amit, who were professors. Okay, so papers about neural network optimization. So I would describe the state of neural network optimization today as follows. On the one hand, we have a number of optimization algorithms that can successfully train neural networks, SGD, momentum SGD, atom. Furthermore, in some simplified settings, like on quadratic objective functions or convex objective functions, we understand what these algorithms do. We get why they work. But when it comes to like neural network training, we really have almost no understanding of how these algorithms like actually function when you let them loose on a neural network training problem. So what we do in this paper is we take a close look at what I would argue is the simplest optimization algorithm, which is full batch gradient descent. And we show two things. First, we show that across many different architectures and tasks, the behavior of gradient descent seems to obey a very simple characterization. And second, it's not what you think. What I mean is that this characterization is somewhat at odds with some conventional wisdom in the optimization, in optimization regarding how gradient descent is supposed to function. Okay, so let me just preview the characterization. How do I remove the bar on the right? Okay, so let me preview the characterization. So the whole thing revolves around this quantity we'll call the sharpness, which is the maximum eigenvalue of the Hessian matrix of the training objective. So to illustrate the phenomenon, let me just run gradient descent using the step size eta equals 0.01. On the top, I'll plot the evolution of the train loss. On the bottom, I'll plot the evolution of the sharpness during training. Now, this orange dashed line marks the special value 2 over eta. And since eta is 0.01, 2 over eta is 200 here. Now, the significance of this value is that gradient descent is unstable whenever the sharpness is greater than 2 over eta, where eta is the step size of gradient descent. And I'll explain momentarily where that threshold comes from and what I mean by unstable. Okay, so let's train. Okay, so what happened? First, we see that the sharpness rises all the way to the dashed line, which marks 2 over eta, during which time the train loss is decreasing monotonically. Then, once the sharpness reaches 2 over eta, it then spends the rest of training hovering just above that value, during which time the train loss is no longer monotonically decreasing. It's now behaving non-monotonically, although it is decreasing over long timescales. We call that latter regime the edge of stability. And our main finding, and our paper, this is an empirical paper, our empirical finding is that gradient descent typically operates in this regime when you're training neural networks. Now, this finding has some implications for the theory of neural net optimization. First of all, it cast doubt on some conventional wisdom regarding step size selection. Second, it cast doubt on the utility of like quadratic Taylor approximations as a model for the local progress of gradient descent. And finally, it cast doubt on certain convergence analyses for gradient descent, in particular, those that aim to prove that the training objective decreases monotonically, or those that assume the condition called L-smoothness. So I'll talk about all this more later. I just want to preview why we might care about these findings. Okay, so before I get to the neural net stuff, let me just give some background information about how gradient descent behaves on quadratic objective functions. So this is where you're going to tell this is where I'll convey what I mean by unstable and where the 2 over eta magical threshold comes from. Okay, so let's start with the one-dimensional quadratic objective. So let's think of an objective function of the form f of x equals 1/2 ax squared plus bx plus c, and assume that a is greater than 0. So it is just a smiley face parabola. Okay, now consider running gradient descent with step size eta on this function, starting from like the red dot. So it's very easy to show that the behavior of gradient descent depends entirely on the relationship between the step size eta and A, which I'm calling the curvature. So A is the second derivative. And because this is a quadratic function, the second derivative is constant everywhere. It's just A everywhere. So the behavior gradient set depends on the relationship between eta and A. On the one hand, if A is less than 2 over eta, in other words, if the curvature is sufficiently small, then gradient descent converges to the global optimum. So it goes like this. On the other hand, if A is greater than 2 over eta, so if the curvature is too big, and now I've tweaked this quadratic so that A is now greater than 2 over eta, the gradient descent diverges. This happens. And it's just easy to show using algebra that these are the two cases that happen when you run gradient descent on this quadratic function. So it turns out the same thing generalizes to the case of a multidimensional quadratic. So a multidimensional quadratic looks like this. So the form f of x equals 1/2 x transpose A. A is now a matrix, x plus b transpose x plus c. And the reason why multidimensional quadratics are interesting is because given any objective function, say like a neural net training objective, you can take the second order Taylor approximation around any point, and that gives you a multidimensional quadratic function that's a local model for the training objective. In which case A is going to be the Hessian matrix of the training objective at the point around which you're Taylor expanding. Now, the result, the way that the previous slide generalizes to the multidimensional case is that here, if any eigenvalue of A exceeds that magical threshold 2 over eta, then gradient descent will diverge along the corresponding eigenvector. So this quadratic has two eigenvectors, Q1 and Q2. Suppose that the eigenvalue corresponding to Q1 exceeds 2 over eta. When we run gradient descent, this is what's going to happen. So it's diverging along the direction Q1. It's converging along direction Q2 because the eigenvalue for Q2 was below that threshold. But for Q1, the eigenvalue was too big. There was too much curvature in that direction. And so we're diverging along that direction, and that we're oscillating along that direction with constantly increasing magnitude. And for a quadratic function, you'll just go off to infinity. Okay, now let's talk about neural nets. So recall that the sharpness is our name for the maximum eigenvalue of the training objective's Hessian. And there's a different sharpness for every point in parameter space. So given any set of network weights, there's an associated sharpness. Recall from the previous slide that at any point in parameter space where the sharpness is greater than 2 over eta, that is, where the Hessian of the training objective has an eigenvalue greater than 2 over eta, we know that gradient descent would diverge if you suddenly started running it on the quadratic Taylor approximation around that point. So the question, though, is how does the sharpness behave in neural net training? And so that's sort of the question that our paper answers empirically, in an empirical way. The first finding is that the sharpness tends to increase whenever possible. So what do I mean by whenever possible? I mean, so long as gradient descent is stable, i.e. so long as the sharpness is less than 2 over eta, the sharpness tends to increase. So the sharpness always wants to increase, and it increases whenever it can. That's an empirical finding. It's very robust across all these different architectures and tasks. Let me illustrate this. So I'm going to train. So what this means is if we train with a very, very small step size, then the 2 over eta threshold is going to be very big, and the sharpness will just keep rising throughout all of training and will never decrease. So let me illustrate that. Here I'm going to train that same network from before, but at a small step size, the small step size of 2 over 600. So 2 over eta is now 600, which I've drawn the brown dashed line at. And when we train at this step size, and I'm going to train to completion, which is like, I don't know, defined as 99% training accuracy or something. Okay, so we reached 99% training accuracy, and you can see the sharpness just rose all the way to throughout training. There was a brief dip. If you look closely, there's a brief dip at the beginning, actually. That's why we phrase this as the sharpness tends to increase. as opposed to the sharpness always increases. It's not always true. Sometimes at the beginning there's a dip, but the overwhelming tendency is for the sharpness to go up. It always wants to go up. And if you're interested, so this another paper conjectured that a similar thing might be true for SGD. That's relevant related work, but it's not. I'll talk about SGD later at the end. It's not actually clear what's going on for SGD. We can say for sure that this happens during full batch gradient descent, but SGD is a different can of worms, which I'll talk about later. There is one thing I should mention is there is a corner case, which is that when you're training with a cross entropy loss, the sharpness actually does drop at the end of training, but it's at the very end, and so you should see it as a corner case. This was with square loss, so the sharpness rose throughout training, but with cross entropy, it drops at the very end. But view that as a corner case. In general, it always wants to rise. Okay, the thing that differs from situation to situation is like how much does the sharpness rise? In particular, so first of all, according to neural tangent kernel theory, if you have a network that's parameterized appropriately and that's infinitely wide, the sharpness doesn't move at all during training. And indeed, consistent with that theory, we find that as the width gets larger and larger, the degree by which the sharpness rises shrinks. So the sharpness rises a lot for a narrow network, rises less for a middle width network, rises very little for a wide network. However, the point is that standard architectures that people use, like VGG and ResNet, are in the width regime, are sufficiently narrow that the sharpness rises by like this hugely astronomical amount when you let it, meaning when you train with a small enough step size. So here I'm training a VGG with batch norm on CFAR10 using gradient flow, which is gradient descent with an infinitesimally small step size. Just think of gradient flow as gradient descent with a step size small enough that the 2/eta line, that the dashed horizontal line, is at infinity. So it never becomes unstable. So we're letting the sharpness rise as much as it wants to. And indeed, so in the middle, I'm plotting the sharpness. You can see the sharpness rises from 6.3 at initialization to 2227.6. That's at its peak before dropping at the end because I'm training with cross entropy. So it rises by this hugely astronomical amount once we let it. So this is what happens with small step sizes. Actually, maybe I should pause. Do people have questions? If you have a question, maybe just unmute yourself and start talking because I can't see the chat.
Is the drop in sharpness always after the point at which the test error levels off?
I'm not sure. I haven't taken a close look at like the you're talking about with cross entropy loss?
Yeah, so here we see a drop in sharpness at the end of training, but it's well after the test loss has leveled off.
Yeah, in general, the sharpness will start to drop once. In general, it happens like once the predictions are no longer changing. So I can talk at the end I can discuss why we know why the sharpness drops at the end. It has to do with the curvature. It has to do with the second derivative of the logistic loss function.
Makes sense.
We have an appendix in our paper where we talk about that, but we actually do have a very good understanding of why it drops at the end.
What happens if you reject steps that increase the cost?
That's a good question. If you reject steps that so every step increases the cost. But you mean what happens if we take the step direction that the negative gradient yields and we project out the component of that vector that would increase the sharpness?
A very simple modification of gradient descent, which is always supposed to reduce the cost on each step, is to reject steps that you evaluate the cost and it goes up. If you're minimizing here.
Well, first of all, here I'm the sharp. What I've shown so far on this plot is the training objective is monotonically decreasing. So all the steps for this network, all the steps cause a decrease in the training objective.
Right. I was talking about the previous slides where you were at the edge of stability and going boink, 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 boink.
Yeah. If you reject steps that I don't know what would happen if you rejected steps that would increase the yeah, I don't know what happened. Keep in mind that this is not SGD, this is full batch gradient descent. But yeah, if you could in theory do, well, actually no, it doesn't make any sense because there's no randomness. Yeah, there's no randomness here. So there's no, if you reject a step, the step will be the same as the next, it'll be the same step. Like there's no random, yeah, there's no randomness. So you can't, it doesn't make sense to reject steps.
Okay, so that gets us into adaptive step size, which you're not going to talk about.
I will talk about that later. Okay, I'll talk later about what happens, because you might say, well, it's bad. Like, what if we drop the step size? You might say, drop the step size to ensure stability. Is that what you're sort of proposing?
A very simple adaptive step size is drop the step size if the step is good, or excuse me, if the step is bad, and increase the step size if the step is good.
Sure. Yeah, you can, yeah, I'll get to that later. But yeah, good question. Okay, so let's talk about larger step sizes now. So in the previous slide, I ran gradient descent at a step size that was small enough that the sharpness never rose all the way to 2/eta. Now let me train it at a larger step size, for which the sharpness will cross that 2/eta threshold during training. So this is the same network, but because eta is bigger, 2/eta is smaller. So we're going to hit that threshold. So we train, okay, we've crossed the threshold in the middle of training. So the question is, what's going to happen next? At this point, the Hessian matrix, we know that the Hessian matrix has some eigenvector Q1 whose eigenvalue is greater than 2/eta. So we know that if we were to suddenly switch from running gradient descent on the real objective to running gradient descent on the quadratic Taylor approximation, then the iterates would diverge along that direction. They would oscillate with ever increasing magnitude until they just went off to infinity. That's what happened if we were in gradient descent on the quadratic Taylor approximation. So what happens when we run gradient descent on the real objective, starting from here? So here I'm plotting for the next 200 steps after we cross that sharpness threshold. I'm plotting on the top, I'm plotting the train loss, and on the bottom, I'm plotting the inner product between Q1, which is the largest eigenvalue, largest eigenvector of the Hessian, and xt, which is the iterate. And so that inner product is just the coordinate for eigenvector 1 if you were to express the iterate in the basis of the Hessian eigenvectors. So basically, this is the thing that we'd expect to blow up if we were running gradient descent on a quadratic function, on the quadratic Taylor approximation. And sure enough, it does blow up. So here I'm, you can see that starting several steps after the sharpness crosses that threshold, the iterate starts to oscillate with ever increasing magnitude along the direction Q1. So we start to oscillate, and those oscillations grow in size. Note the changing y-axis scale. They grow in size until they get big enough that they cause a spike in the overall train loss. So at this point, it looks like we're about to diverge. On a quadratic, we would diverge, and it looks like we're about to diverge on the real neural net training objective. And so at this point, it's anybody's guess what happens next, basically. I mean, you can think of, we're basically, at this point, we're running gradient descent outside the parameters of the instruction manual. You're not supposed to run gradient descent in this regime. So you might say, okay, maybe gradient descent is gonna just diverge entirely. Like maybe the loss will go 1, 10, 100, 1,000, a million nan, and it'll just diverge. Or you might say, well, maybe gradient descent is just gonna stall at this current loss value, jump around that current loss value, fail to make any progress. Or you might say, okay, maybe this gradient descent will just like jump off to like some flatter region where the sharpness is sufficiently small, and then it'll just stay there for the remainder of training. So a priori, any of these outcomes are possible. In reality, none of these three things occurs. Instead, what happens is very consistent across all the neural networks that we've looked at. What happens is this. So here I'm going to extend this plot for the next like 600 iterations. Okay. So we can see that immediately the oscillations in this value, which is, remember, it's the coordinate of x. It's basically the part of, it's how much does the iterate align with that direction, Q1. Those oscillations, they look like they're going to blow up, but then they start to dampen. and simultaneously the train's loss comes down. So we sort of step back from the brink somehow. And this is because we're not optimizing a quadratic. If we were optimizing a quadratic, we would diverge. But since it's a neural network, we somehow come back from the brink. And then after that, you can see that the oscillations in this quantity, and this is, remember, this is the basically how much does the iterate, this is the part of the iterate that aligns with that direction, that high curvature direction. It sort of alternates between exploding and dampening. And the train loss behaves non-monotonically, but it's decreasing over long time scales. So we call that regime the edge of stability. That was just a zoomed in portion of the edge of stability. So to recap, what happens overall is first the sharpness rises till it reaches 2 over eta, and then you're at the edge of stability, where the hallmarks of the edge of stability are, number one, that the train loss behaves non-monotonically over short time scales, but it decreases over long time scales. And number two, the sharpness hovers just above the numerical value 2 over eta. Now, okay, here's something cool. At the edge of stability, the sharpness is still trying to increase further. It still wants to go up, but it's being restrained somehow from doing so. What I mean by that is if we were to cut the step size so that now the stability threshold goes higher, the sharpness is free to increase again, and that's exactly what happens. So let me do an experiment. At iteration 6,000, which is when we're comfortably at the edge of stability for that orange step size, I'm going to cut the step size from 2 over 200 to 2 over 300, which is the green step size. So the green dashed line is the stability threshold for the new smaller step size that I'm going to switch to at iteration 6,000. Okay. So here's what happened. As soon as I cut the step size, the sharpness started to increase because it was being held back from increasing previously, and now that restraint was removed, and so it always wants to go up, and so now it returned to its rise upward. Simultaneously, if you look at the train loss, the minute we dropped the step size, the train loss started decreasing monotonically again. And then it became non-monotonic once we reached the edge of stability for the smaller green step size. So what I like to think of this is as like you can basically interpret gradient descent at the edge of stability as performing constrained optimization. So gradient descent we typically think of as like an unconstrained optimization algorithm. I mean, in the field of optimization, you have constrained algorithms. Gradient descent, vanilla gradient descent is not one of them. It's an unconstrained algorithm. But actually at the edge of stability, it basically behaves like a constrained optimization algorithm. We say explicitly minimize f of x using gradient descent with a fixed step size eta. But what that implicitly gets executed as is minimize f of x subject to this constraint that all the eigenvalues of the Hessian must be less than 2 over eta. So it's an implicit constraint. So gradient descent is implicitly acting like a constrained optimization algorithm. And you can think of it as the constraint is active at the edge of stability. So the dynamics of the optimization algorithm implicitly enforce this active constraint on the sharpness that's constantly active. Because if we relax the constraint, it gets violated. Okay, so I've showed you so far just one network, one step size. Let me show you some more, because this is an empirical paper, I need to show you more evidence. So here, same network, square loss, varying the step size. Previously, I showed you the orange learning rate. Now I'm showing you a whole sweep of learning rates. You can see that for each learning rate's a different color. You can see that for each learning rate, sharpness rises until it reaches 2 over eta, and then it plateaus there. Now the purple learning rate is sufficiently small that we never reach 2 over eta. So we avoid the edge of stability, and we just decrease monotonically for the entirety of training. But the thing you should note is that the purple learning rate is not a good learning rate. It's you train slower at the purple learning rate than at any of the others. And in fact, and this is something that we find generically true, which is that at the step sizes that are small enough to avoid the edge of stability, those are suboptimal step sizes from the perspective of training speed. And they also don't generalize any better. So in practice, you would never use those step sizes. And in fact, I'll show you in a second, is for real networks on real data sets, this phenomenon is exaggerated so that small step sizes, the step sizes that are small enough to avoid the edge of stability are just ludicrously small on real networks. This is not a real network. This is just a fully connected net. on a 5,000 size subset. So for this network, the purple step size it's suboptimal, but it's reasonable. But for the real networks, it's not even reasonable. So that was square loss. This is cross entropy loss. So same thing happens, although two differences are: one, at the end, you can see that the sharpness drops because we're using cross entropy. And again, we have an explanation for that. We actually do have a recursive explanation for that in the appendix. We don't know why it rises otherwise, but we do know why it drops at the end in cross entropy. And finally, yeah, and the other difference is that the phenomenon is a little less crisp with cross entropy. Like there's more of a gap between the sharpness and the line 2 over eta, but still it rises. It's always like basically just above 2 over eta, even if the definition of just above differs between the square loss and the cross entropy loss case. Okay, here are real networks on the full CFAR10 data set. So I'm using a VGG without BN on the left, a VGG with BN in the middle, and a ResNet on the right. And you can see that, yeah, for each step size, sharpness rises until reaching 2 over eta, and then hovers just above that value, except with cross entropy loss at the end, it sometimes drops. Yeah, and for these networks, the sharpness actually rises extremely fast. So for the VGG with BN, for example, if you wanted to train to completion at a step size that was small enough to avoid the edge of stability, they would be suboptimal in terms of iteration count by a factor of 50. So it would take 50 times as long to train at that small step size than at a better step size. So what I'm trying to get at here is that, like, you should think of the edge of stability as the rule rather than as the exception. Edge of stability is the rule. The plots like that purple step size on the previous slide, where you remain below 2 over eta for the entirety of training and you train loss decreases monotonically, that's the exception. That's what I'm trying to convey. Okay, here's more tasks. Here's a synthetic, on the left, I have a synthetic regression task. On the middle, I have a deep linear network. And on the right, I have a transformer on like an NLP task. Always the same thing. Okay, this is cool. So gradient descent is often combined with momentum. There are two kinds of momentum. There's Polyak style momentum and there's Nesterov style momentum, named after their inventors. And what these actually are, basically they're just different. They're just two different update rules, two different ways of combining the momentum term in with the main gradient descent update. The details aren't relevant, but what's relevant is that what's interesting is that basically for momentum gradient descent, we also find that the sharpness equilibrates just above the maximum stable value. But what's interesting is that for momentum gradient descent, the maximum stable value is no longer 2 over eta, it's something different. So for a Polyak style momentum with coefficient beta, the maximum stable sharpness is given by this expression. Rather than 2 over eta, it's 2 plus 2 beta over eta. For Nesterov style momentum, this is the maximum stable sharpness, this other expression. So now let me show you what happens when you run momentum gradient descent. So first, let me do vanilla gradient descent. This is a vanilla gradient descent with step size 0.01. So like we saw before, it equilibrates to 200. Okay, now let me try gradient descent with Polyak momentum. So same step size, but let me add Polyak momentum with beta equals 0.2. So the brown line, the brown dashed line, is the maximum stable sharpness for that algorithm, for gradient descent with Polyak momentum of 0.2 and step size 0.01. You can see when we train, sharpness rises all the way to that value, hovers just above that value. Now here, let me do Nesterov momentum with beta equals 0.2. So what's interesting is that Polyak momentum actually increases the sharpness threshold. Nesterov momentum actually decreases the sharpness threshold. I don't have an intuitive explanation for that, but that's just what the math comes out to. And sure enough, if we run Nesterov momentum, you can see that it sharpness is predictable. So this is like a fun, this is Polyak with beta equals 0.05. And this is Nesterov with beta equals 0.05. So it's like a fun parlor trick. You can basically numerically predict what value the sharpness is going to take on, which is cool because like in deep learning, you can't really predict anything numerically. Yeah. So I can talk more later if you want, if you're curious about like which you can't do this parlor trick with every optimization algorithm. Only certain optimization algorithms you can do it for. In general, the dynamics of the sharpness are not like crisply predictable, even in the full batch case. It's only for special algorithms that they are. Okay, let me talk about some implications for optimization theory. So the biggest implication is for like the theory of like step size selection. So the conventional wisdom says that in order for gradient descent to function properly, you need to make sure that the step size is strictly smaller than 2 over the sharpness. So, and that's just conventional wisdom everywhere, but here's an example of it. This is from a paper by Yann LeCun and Leon Bautou and collaborators from the 90s called Efficient Backprop. It's like a very well-known paper. And here you can see the snippet. They're telling us that if you're going to have a single scalar learning rate for all rates, that is, if you're using like gradient descent, then you need eta to be less than 2 over the largest eigenvalue of the Hessian in order to avoid divergence. This is the conventional wisdom. So is it true? So actually what we've seen is at the edge of stability, the sharpness is just a bit greater than 2 over sharpness. Sorry, the step size is just a bit greater than 2 over sharpness. And yet somehow gradient descent does not diverge. Now on a quadratic, we would diverge, but on the neural network, we don't diverge. So you can say, well, that's like, I don't know how surprising that is because it's just a little bit greater, you know, it's not a lot greater. But in fact, we can moreover say that it's actually not, it's not a bad thing that the sharpness, it doesn't seem to be bad that the sharpness is greater than, there's a little bit greater than 2 over the step size. It's actually good. What I mean by that is we've done experiments where, so at the edge of stability, you can imagine, like the conventional wisdom would say, if you're at the edge of stability, oh, you're unstable, you should drop the step size so that you recover stability. Actually, that when you try that, that just makes you train slower. So at the edge of stability, you could drop the step size, but it's not a good idea because then you just train slower. And also you later wind up at the edge of stability. Now, what you can do is you can sort of adaptively anneal the step size so that you, this sort of goes back to the question from before. So you can sort of, what you can do, what we tried in one of our appendices to our paper is you can dynamically anneal the step size. So like what we did is we tried setting the step size to, so again, there's no notion of accept, reject, because this is a deterministic algorithm. But what you can do is you can sort of say, okay, at every iteration, I'm going to compute the sharpness, and I'm going to set the step size to be 1 over the sharpness, which is 1 over the sharpness is sort of optimal in some cases. So that's often a rule that people recommend. So we tried dynamically setting the step size to be 1 over the sharpness and recomputing the sharpness. It doesn't work well. It's just underperformed. So that algorithm is basically, I don't have the plots here. I think I might have them in a later slide. That algorithm is basically, it's stable. So the train loss decreases monotonically, but it's bad. It trains slower than the edge of stability learning rates that give you non-monotonic train loss. So basically the stability is just not that important. And you can say, oh, well, 1.0 is very small. Well, I've also tried, I compared the 2.0, or sorry, I tried a heuristic where you set the learning rate at each step to 1.9 over the sharpness, which is almost as large. I mean, 2 is the maximum, right? So 1.9 is almost as large as you can get without diverging. And when you, sure enough, if you have this dynamic 1.9 over sharpness learning rate rule, then yes, it's stable, but it basically underperforms fixed step sizes, which are unstable, or which are edge of stability, because the stability just doesn't matter. Moreover, even bigger than that, the other issue with the conventional wisdom is that like the sharpness, if you like measure the sharpness in the middle of training, it doesn't give you any information at all about how the step size ought to be set. Instead, it just tells you about how the step size is currently set. So the conventional wisdom says the sharpness should convey some information about how you should set the step size. Actually, no, the sharpness is just a mirror reflection of your current step size. It tells you nothing about what other step sizes are possible, or which are good or which are bad. It's just a mirror reflection of your current step size. So I like to think of it as the situation is sort of well described by this like meme template that's become popular. So it's, if you just learn what gradient descent is, and someone asks you how do you set the step size, you would say like, oh, make it big, because then you'll go fast. If you take a class and you learn about how to analyze gradient descent, then you would say, oh, no, you can't just make it big. you have to make sure that throughout the entirety of training, the largest eigenvalue of the training objective Hessian remains strictly less than 2 over the step size to ensure stability. That's like the smart answer. Actually, though, the reality is that you just make it big. Because empirically, we find that for full batch gradient descent, bigger is just better. Now, I'll add the caveat, this is only for full batch gradient descent. For SGD, you actually can't make it. Big step sizes don't work because there's a noise problem. So this is just full batch, which nobody uses. So take this, don't take this slide and then go off and just make your learning rates as big as possible because it won't work because you're using SGD. But if you were using full batch gradient descent, you should do that. Just make the learning rate very big. And don't worry about the sharpness. So here's another way of like thinking about that same principle, or yeah. So it's basically deep learning is like very topsy-turvy. I like to think of it as it's like those like in Soviet Russia jokes. Like there are those, that there's that joke format like in Soviet Russia, and then it's like the thing is reversed. So it's like in the USA, you watch television. In Soviet Russia, television watches you. So the joke is that it's reversed. That's basically the relationship between sharpness and step size in deep learning. In classical optimization, the sharpness determines the step size. In deep learning, it's the other way around. The step size determines the sharpness. It's totally topsy-turvy from what is taught in optimization classes. So there are some other implications for optimization theory, and I'm about to conclude and take questions. So at the edge of stability, another implication is that like at the edge of stability, so the quadratic Taylor approximation is actually like a very poor model for the local progress of gradient descent, because as we've seen, whereas gradient descent would diverge on so at any point where you're at the edge of stability, gradient descent would diverge if we switch to running on the quadratic Taylor approximation. But on the real objective, it doesn't diverge. It instead is successful. So I'm not saying here that quadratic Taylor approximations are useless. They're actually second order methods do work, or they might be slow, but they do work. I'm talking here about quadratic Taylor approximations as a model for the local progress of gradient descent. They don't work. Secondly, so we've seen that at the edge of stability, the train loss is behaving non-monotonically, and yet gradient descent is successful. So this is actually contradicts a lot of convergence analyses for gradient descent. Often you'll see like if you look at like convergence analyses that people publish for gradient descent, they're trying to analyze neural network training. Often there's like a step in the proof where they're like, yes, and like the loss decreases by this amount at every time step. Actually, it doesn't decrease at all in practice. So those convergence analyses can't be right because the loss is non-monotonic at reasonable learning rates. So those convergence analyses, again, they can conceivably describe those super small learning rates. But remember that for a ResNet on CFR10, that super small learning rate is going to be suboptimal by a factor of 50. So no one would ever use that learning rate. The real learning rates, training loss is non-monotonic. And finally, there's like a thing called L-smooth. If you get into like optimization, there's like a condition called L-smoothness. And there's this like trend in the literature that people analyze neural network optimization under this assumption of L-smoothness. And it's clearly, I won't get into details because I want to wrap up, but that's clearly violated at the edge of stability because the minimal you have to, those are also assuming that the sharpness is less than 2 over the step size. Here, the sharpness is actually greater than 2 over the step size. Okay, so the conclusion, and now I'll take questions, is that when training neural networks using full batch gradient descent, the sharpness behaves in a manner that's both, 1, surprisingly predictable, and number 2, surprisingly different from the conventional wisdom. And I also want to give the warning, be careful about taking stuff you learn here and trying to apply it yourself, because this is all for full batch gradient descent. I should talk about SGD. People are probably curious about, let me just do 2 minutes on SGD. So here I'm running SGD and I'm plotting the evolution of the sharpness. So here I'm running SGD, so same learning rate, but different batch sizes. So the blue batch size is 5,000, which for this problem is full batch. There are 5,000 training examples. Then orange is, I actually can't read the label because that bar is in the way. I can't move it, but orange is smaller, green is smaller still, and so on and so on. Pink is the smallest. You can see that during SGD, the sharpness, first of all, it doesn't, so for SGD with large batch sizes, sharpness basically behaves like full batch gradient descent. Sharpness rises all the way to 2/eta, or in the green case, it's like just below 2/eta, and then it hovers there. But for like small batch SGD, doesn't rise to 2/eta, and moreover, there's not going to be a formula for, oh, this is the SGD with batch size 100, the sharpness equilibrates at this formula, which is some function of the step size and the batch size. That's not possible because you can sort of, often during SGD, the sharpness doesn't settle at any value at all. So in these examples, it just keeps rising constantly, but there are also other examples where it sort of just it drifts downward throughout training. So for SGD, there's no pattern. But I will say, if you take any of these SGD plots and you were to imagine suddenly changing to full batch gradients in the middle, you would see the sharpness instantly start to rise until reaching that 200 line. But yeah, so it's basically, but this is, you can't assume that anything I've said has any relevance for SGD. So that's a disclaimer. This is just about what would happen if you were training using full batch gradient descent. And to some extent, I think that these findings have not been noticed till now because nobody does train using full batch gradient descent. Okay. Questions? Let me see if I can read. Oh, let me just cancel this. Okay, now I can read the chat. Okay, Ria asked, does this imply adaptive weight specific? So the question is, does this imply that adaptive weight specific optimizers like Atom are somewhat better options? I don't know. I don't think, I would not feel comfortable. Or better options. Yeah, I basically don't feel comfortable drawing any conclusions like that. Although Atom is an example of an optimizer for which there's the sharpness doesn't settle at any fixed value using Atom. So you can't predict the sharpness mid-training, like when you're using Atom, it doesn't work. There's no pattern. Yeah, I don't know if Atom's better or not. So Jeff asked, is there a relationship between this behavior and the activation function? So we tried this. Our paper is, despite it being a purely empirical paper, our paper is 80 pages long because we have like 60 pages of like plots where I just demonstrated this for like every conceivable permutation of like, activation function architecture that you can think of. So yeah, it happens for all the activation functions. It doesn't, this happens, we tested, I tested like ReLU, LU, tan H, soft plus maybe, I don't know. I tested like 5 different activation functions. This happens for all of them. Now, again, the particulars might differ from network to network. In particular, the amount by which the sharpness rises can sometimes differ from network to network. Like for some networks, it rises a lot. Some networks, it only rises a little. If it rises a little, the range of like learning rates that are going to be edge of stability, like the range of learning rates that you're going to like catch that stability threshold in the middle of training are going to be quite small. But for realistic networks, they're very large, meaning the range is large, meaning like every step size is edge of stability, basically. Okay, Pratyush asked, does this mean that neural networks never diverge? No, they do. You can, if you trained at anything larger, they would diverge. Like, no, they do diverge with full batch gradient descent. It's just that it's not predictable from the sharpness, and it's much the learning rates at which they would diverge are much greater than what you would expect just from looking at the sharpness.
So, do you detect saddle points when you're looking for the sharpness?
So by saddle points, you mean like, do you mean like negative eigenvalues?
Negative, A's or whatever you want to call them.
Yeah. So I mean, in general, A is always A will have negative. The Hessian always has negative eigenvalues when you're training neural nets, but they're generally small.
So the local quadratic model can have both signs of eigenvalues.
Good point. Right. So so there's a good point here, which is that right. So on the local quadratic model, correct. So when you're running gradient descent on the local quadratic model, if there are negative eigenvalues, which there always are, then you diverge, you will also diverge in those directions, assuming your step size is positive. So you will always, right, so gradient descent on a quadratic with negative eigenvalues always diverges. That's true. So it's, yeah, but empirically, it seems like the negative eigenvalues don't contribute to divergent behavior. They don't cause instability on real neural net training objectives. In that sense, so I mean, so let me explain again. So for any fixed learning rate, there are two different kinds of eigenvalues that cause you to diverge. One is eigenvalues that are greater than 2 over the learning rate. The other is eigenvalues that are less than 0. Empirically, only the first kind of eigenvalue seems to affect the behavior, seems to have any relationship with the behavior of gradient descent on the neural network training objective. Meaning a too large positive eigenvalue does cause edge of stability behavior, but the negative eigenvalues don't cause anything. It seems like those directions of like negative curvature are like illusory, in that if you actually if you start walking, and if you take one of those negative eigenvalues and eigenvectors and you start walking in that direction, you will find that the quadratic Taylor approximation gets inaccurate real quick.
So back in the old days, when we had smaller networks, people like me tried to do second order gradient descent.
Mm-hmm.
And the phenomenon that you see is improvements of the cost were chunky. It would sit at a plateau for a while and then go down, and sit at a plateau for a while and then go down. And my explanation for that, never tested, was it's just going from one saddle point to another. As it goes down. Every time you take a big step down, in some sense, everything rotates, and you have to figure out what the new directions are. And then you end up making that big step, and then everything rotates. Have you thought about of what would effectively be second order gradient descent algorithms?
So all I can say is that, like, in my experience, which is training like first order methods on like, the neural networks today are also different from the neural networks that you might have been playing around with. Like, I think our understanding of
Yes.
I was using, again, many of the experiments were with fully connected networks, but I'll say that our understanding of like initialization is better now. So everything that I just presented was using standard initialization schemes. So it may be the case that with the standard initialization schemes of today, the problem you're talking about, where you have these like long flat periods where there's basically no gradient, goes away. It's possible that they've been fixed by improvements in initialization over the years. But I've never seen what you're describing, which is where, although I'm using, but I mean, you would sort of expect the same. I believe you would expect the same thing to hold for gradient descent, where you have periods of like. Yeah, basically, I've never seen anything like that for gradient descent, and I believe that the reason why you're seeing it is either due to like bad initialization, or due to like like finicky details of the second order algorithm, like how you like, it's possible that it might have been caused by like issues with, because with second order methods you have to be very careful. You have to like, so that you don't take huge steps, because small eigenvalues would lead you to take huge steps. So you need to like, there are also kind of hacks that avoid that. So it might have been one of those hacks that caused the behavior you're talking about.
Yes. I mean, some of the hacks are very simple. You just reject things that go uphill. This leads to the question of what happens when you do line minimization. You pick a direction for the gradient descent, then you minimize along that line.
So line search, you basically, when you do line search, the sharpness keeps rising. So that's what happens to the sharpness. In fact, for an earlier draft of the paper, we were gonna, demonstrate like what happens to the sharpness when it, basically, line search, when you run gradient descent with line search, sharpness just keeps on rising and rising. Now, I do want to give the caveat that like in the deep learning literature, there's this like widespread belief that there's something called sharpness and that sharpness is bad for generalization. I'm not using, in this paper, we're just defining sharpness to mean largest eigenvalue of the Hessian, and we're not claiming that this has any relationship at all to generalization. Like that story is very murky, and I'm not claiming, so don't go home from the talk thinking like, oh, if I train at larger learning rates, it'll find sharp, flatter minima, which ergo will generalize better. Don't draw that conclusion, because I'm not using sharpness. I'm claiming no connection to generalization.
When this gets into the media, you're going to totally lose control of all those caveats.
That's true. So Jeff asked, would it be possible to explicitly regularize the largest eigenvalue of the Hessian? Would the behavior of the resulting algorithm be similar? Would it help in real deep net training? Frankly, I mean, explicitly, I mean, there's no need to explicitly, I don't know how you would enforce an explicit constraint. I mean, it seems like the best way, if you want to enforce a constraint on the largest eigenvalue, just pick your step size appropriately. And that's the way that you can basically enforce the constraint.
I guess I was thinking that it would be interesting to be able to decouple step size and this regularization so that we could independently see their effects.
Yes, good point. Although I want to add the caveat that I don't know if this is useful regularization. It is like an interesting implicit bias on the training that you're constantly being blocked from going in these certain directions. I did not see strong evidence in my experiments that it's good for generalization, so that this is a desirable thing from the perspective of test performance. Yeah. So
I think we could actually efficiently compute that regularizer, right? Because you can find the largest eigenvalue with power iteration much faster than quadratic.
Mm-hmm. Yeah, I mean, that's how I was using power iteration to show up for all these plots. I mean, if you want to regularize it, it would be, so I mean, I guess, I see what you're saying. You just need to compute the gradient of that. Yeah, so the closest, I didn't try that, but I tried something very similar, which is I was just curious what happens if you ran gradient descent, but projecting out the component of your ordinary gradient that causes the increase in the sharpness. So in particular, which is you're projecting out, I mean, doing that to first order, which just amounts to you compute the gradient of the sharpness and you project that vector out from your ordinary, your data set gradient.
So this would be the same. Sorry, this would be the same thing, except you only do it when the sharpness is above a threshold.
Well, that's what I was doing. Although you're proposing, so it depends what you mean by regularize. Yeah, a constraint version would be exactly what I was doing. Yeah. A penalty version would be, instead of projecting that sharpness gradient out from the regular gradient, you just add it, or you subtract it from the regular gradient, I guess.
So I'd imagine those would be similar. So what happened?
So what happened is just you optimize slower. So basically you can train the network without increasing the sharpness, which makes sense, because there existed flat solutions of widely different. I mean, to find a flat solution, all you need to do is train with a large learning rate. So we knew they existed, and sure enough, if you project out the direction, the gradient of the sharpness, so you can still train successfully, but you train slower, because basically what's happening is that like that component of the gradient that increased the sharpness was also good for decreasing the loss. So you just train slower. You still train successfully, but just a little slower, because you're no longer getting that. Yeah, so so I have no useful perspective on like, do these solutions that do going in these directions that increase the sharpness, is that good for generalization, bad for generalization? I have no opinion. All I know is that it's obviously good for training, because otherwise, because if it weren't, gradient descent wouldn't go in those directions in the first place. So when you remove those directions, you train slower.
Cool, thank you.
Mm-hmm. Any other questions? So Oscar asked about the other eigenvalues. So I've only talked about the largest eigenvalue, but I don't have the plot here. Yeah, so in one of the appendices to the paper, we look at the other eigenvalues. And basically what happens is that like, basically this process happens with the next several eigenvalues. So if you monitor if you basically, let's say you look at the top 5 eigenvalues, what happens is that like, so they all, at the beginning, they all rise. Then when the top one, which is the sharpness, crosses 2 over eta and starts hovering there, the second one keeps rising until it too reaches 2 over eta and then keeps hovering there. And the third one later eventually also reaches 2 over eta and then hovers there. So in turn, all the eigenvalues are all the eigenvalues, the implicit constraint becomes tight for like not just the top eigenvalue, but the top few eigenvalues. But that obviously it's only the top, it's the next few. It doesn't happen. The Hessian's a very big matrix, has a lot of eigenvalues. This doesn't affect the bulk of the eigenvalues. This is just what happens to the top ones.
I see. And the rest of them are like remaining the same, or are they like mostly 0? Or I don't have a good intuition about like what the Hessian looks like.
Yeah.
Like the eigenspace.
Yeah. So first of all, most of them are very small.
I see.
Close to 0. And there are some that are small and negative. I don't have experience looking at the spectrum of the Hessian.
I see.
Because it's expensive to obtain.
Yeah, I know. Yes.
But I do have some experience looking at the spectrum of the neural tangent kernel, which is a matrix that sometimes approximates the Hessian.
I see.
And with that, what you see is the general trend, just in general, is for eigenvalues. Just the matrix just rises in scale during training.
Mm-hmm.
That just seems to always happen.
I see.
And that's basically why, I believe that's sort of why like progressive. That's why the sharpness rises, because all the eigenvalues are rising, because the matrix is just increasing in scale.
I see.
That's what seems to happen. So so the general trend is that all the eigenvalues rise, and what happens but they rise. Yeah, most of them are rising relatively slowly. And so
but only the top ones.
Yeah, so when you hit the edge of stability,
mm-hmm.
It's like the top one stops rising, but the others actually do keep rising.
I see, but like they rise so slowly that it never really.
Yeah, they never reach the 2
okay.
rate threshold.
Yeah, thanks a lot.
Mm-hmm. Any other questions? Okay, cool. Yeah, I'll stick around here for like another few minutes in case anybody has any other questions.
Thanks for a really cool and thought-provoking talk.
Thanks.